And so vector functions were of the form a real valued function of t for each of the components. Okay, and so and we kind of talked about the basics of this. So for every value of t, you get a vector, and if you put all those vectors for different values of t in standard position, then what happened? We let t increase, and we trace the tips of those vectors, which would be the same as the coordinates of the points, right? And we saw that we got what kind of thing? Do we get a surface for that? Curve, right? So yeah, like a path, right? A path or a curve in space. So again, letting t increase and generating the vectors, placing them in standard position, tracing out the tips of those vectors, which are the coordinates of the points in space. We generate a curve. And we started practicing a little bit. We saw that so graphs as a curve. And so we saw a couple examples last time. We said, oh, if x is sine and z is cosine, whenever you pair up sine and cosine to two of the variables, we're talking about an ellipse or a circle, right? Ellipse or a circle. We recognize this vector function as what we had done before when we developed lines. That when we did lines, we were actually doing a specific type of vector function. And so let's take a look at some more examples here. So first of all, this one. T squared, and 3. So this means that x equals t, y equals t squared, and z equals 3. So we want to kind of make heads or tails of this as a graph, as a curve in space. So what do we notice right away that we should focus in on to start?
It should stay on z equals 3.
Yeah, so this means that all this whole curve stays on z equals 3. What is z equals 3? Z equals 3 is a horizontal or vertical plane?
Horizontal.
Horizontal plane up at height 3, right? So this curve is going to live, this vector function is going to live in the plane z equals 3. And now we want to use what we talked about with back in Calc 2. If x equals t and y equals t squared, make heads or tails of that, right? So what does that represent? We can actually combine those. And we just get, if x is t and y is t squared, then what does y equal?
X squared.
X squared, right? So y just equals x squared. And so what do we have? We have, so by doing those two things, we can put it together and say we have the curve y equals x squared in the plane z equals 3. So we know that y equals x squared is our kind of reference parabola. Hey, Jonah, can you turn off your microphone, please? So we've got y equals x squared in the plane z equals 3. But remember, things are kind of turned around in R3. X is out coming at us and y is to the right. So this thing opens on the positive y-axis. So it's going to look something like this. Let's do the pretty version here. So the blue is the prettier version there. Opens up on the y-axis at a height of z equals 3.
And why is it y equals x squared instead of
say x equals y, or why did we choose the x squared?
We didn't choose it, so it's based on taking these two together, right? If x equals t and y equals t squared,
I see.
t is x.
Mm-hmm.
Yeah, so there wasn't a choice. It was determined by these two components. Okay, next one. So this is similar. What can we say right off the bat on this one?
Stays on x equals 2.
Yeah,
Which is
so
a vertical plane, right?
yep, x equals 2 is a vertical plane, right? And where's that vertical plane relative to your screen?
In the front, right?
Yep, it's in front of you, right? 2 units in front of your screen. It's 2 units forward. So something like this. And what do we got living in that plane? So here's say 2. What lives in that plane then? Y equals t. Z equals e to the t.
So z equals e to the y.
That's right. Z equals e to the y, right? So if y equals t, z equals e to the t, then z equals e to the y, living in the plane x equals 2. I'll just go right to the pretty version of that. Something like that. Right, so it lives in x equals 2. The plane, or the curve, z equals e to the y, and x equals 2. So notice this is going to be an important technique, because we're going to start actually writing. So given some conditions, we're going to be writing the vector functions rather than being given the vector functions. So notice what's happening here. This is a really important thing, that you have this thing where one of your variables is t, and then another variable is a function of t, and that's an easy combination, right, then to eliminate t, right? So if you're working backwards, if you had some curve setting one of the variables equal to t, and then the other variable, it would simply be the equation that you have with t in it instead of the variable. Does that kind of make sense? So we'll see examples of this. But if I was trying to write this, the z equals e to the y parametrically, the easiest way to do that is say, oh, just let y be t, and then z would be e to the t. So we're going to see that later in class. We're going to be on the lookout for that. Having to write a basic equation parametrically, if it's not a circle, right? So the exception to that would be if you have a circle and an ellipse. Now you're going to use sine and cosine paired together. But if you don't have a circle and an ellipse and you have kind of a straightforward function of 2 variables, then a good technique to parameterize that is set your kind of this independent variable as t, and then your dependent variable is the same as the formula with a t in it now. Okay, so hopefully that makes sense. So let's look at a more challenging one here. This next one, cosine t, 2 sine t, and t. So what do we notice right off the bat here?
Cosine z and 2 sine z.
Okay, so that would be, yes, that would be doing what we did, but yes. Let's write that down. Cosine z, y equals 2 sine z. Okay, good. But rather than combining with z, do you see what happens if you combine x and y together?
In the ellipse.
Yeah, so if you see, we're on the lookout for, pairs, cosine and sine paired up with variables, okay? And that's what we have here. So it's almost like the unit circle, but I have this 2 here. So what does that do to the unit circle having a 2 there? So it's the unit circle, but it's all the y coordinates are 2 times what they were in the unit circle. So?
Is it an ellipsoid or ellipse or something?
Yeah, a unit circle stretched in the y direction. Times 2. So we're going to take the unit circle, and we're going to stretch all the y coordinates by 2. That makes an ellipse. So let's just forget about z for now. Let's sketch that ellipse. So y is 2 to x is 1. Okay, and then since cosine is defined as the x coordinate and sine is defined as the y coordinate, it's going to be, we're going to have our basic starting from the positive x axis and going counterclockwise. Something like that. So as t increases, we're going around counterclockwise. T is our angle measure, right? T is angle measure. So it's going to sweep out this ellipse. If we're ignoring z, it's going to sweep out this ellipse in like this. And as you keep increasing t, you'll just keep going round and round the ellipse.
So would that just pick a point on the line if you give it a t value?
Yeah, so given a t value, you get a point on the curve for all these.
Yeah.
Exactly. So t equals pi over 4, you're going to get this vector right here, or this point on the curve. And that's true for all vector functions. A particular input value gives you a particular vector, which in standard position gives you a particular point on your curve. Okay, so
And, if not all of the functions were necessarily related or had like a ratio to one or the other, it wouldn't sit on just one plane, would it?
so this one does not sit on this plane. We're still building it up from the ground here. So yeah, like this is not going to sit on a plane, as you'll see in a second. This one sits on a plane because x is always 2. This one sits on a plane because z is always 3. This will not sit on a plane. Because what's happening as we're going around this ellipse, so t increases and we're heading around this ellipse, what's happening to z as we do that?
Oh, it's going up with each.
Up and down with the t.
Right, right. So z is going to increase linearly with t. So not only are we going around an ellipse, but simultaneously we're moving up as t increases. So what kind of curve will we get?
In the comments they said kind of spring shaped.
Yeah, it's called this is called a helix, or a spiral, or a spring. Yeah, and so
Because it keeps going around the circle, but z keeps increasing.
exactly
Or
simultaneously.
decreasing.
Exactly. So this is an elliptical helix. We're going around an ellipse, but t is increasing as we do that, and so we're going to get this spiral shape. And that should make sense. So if we look down, right down in the xy plane, what are we going to see?
The ellipses are going to lay over each other.
You just
Or
see,
at least the outline.
yeah, you just see an ellipse, right? You're just going to see like an ellipse. Okay. So, any questions on that? All right. So, remember when we talked about? So we're doing this thing where we're taking these. Someone also said x equals cosine z and y equals 2 sine z, and so we could actually write this. How could we write this in terms of x and y? We know the unit circle is what? X squared plus y squared equals 1. So how will I adjust the unit circle to get this circle? What will I do to my equation of x and y to get this circle?
Replace x and y with cosine t and 2 sine t respectively.
Nope, I want to keep it looking like this, but I want to.
All you would do is just
Cosine z squared plus 2 sine z squared equals.
Nope, I don't want to bring t into it. I want to leave it just in x and y. I don't want to bring t into it. I want to get, this is the equation of the unit circle. I don't quite have the unit circle. I want to get the equation that I get
Would
when.
it be
We have to divide y by 2.
squared over 2?
Yeah, it's going to be y squared over
Is it over
2
2 squared?
squared, right?
2 squared.
So, because this is just multiplies all my y's by 2 and gives me kind of a y radius of 2. So now I've got these 3 equations. How do each of these equations graph? in R3. So now I've got equation of x and y, equation of x and z, equation of y and z, which are all consistent with my vector function. These all are aligned with my vector function. How do each of these graph?
They're what the graph looks like looking down on each axis.
Okay, but if, yes, that's true. But just say take this equation right here. How does that, just by itself, how does that graph in R3?
So it's
It's just flat. It's on a plane compared to not being in a plane.
No,
Just
you're
cylinder.
assuming that z equals 0, and that's not in the cards here.
They're cylinders.
These are cylinders, right?
Oh, yeah.
Cylindrical surfaces, right? So if just
Oh,
looking at
because
this,
Z isn't- okay.
yeah, so you can assume z could be anything, right? So z is allowed to change, and if z is allowed to change, you get a cylinder. Same with these two. So we know these equations came from our vector function, so what do these cylinders have to do with our curve?
It's the outline, right?
The outline.
I guess it would be the position of where. I guess it would be that ellipse. Would any point's going to fall somewhere on that ellipse?
I think you're thinking the right thing there. So here's that elliptical cylinder. X squared plus y squared over 4 equals 1.
Oh, it's the surface.
Yeah, cylinders are surfaces, right? Cylinders are surfaces. So our curve, since this surface came from our curve lies on that surface, right? We got this surface from this relationship, ignoring z. And so all the points on our curve are going to lie on that surface. Likewise, all the points on our curve are going to lie on this surface, this sinusoidal cylinder. Let's draw that. So there's a sinusoidal cylinder, x equals cosine z, the turquoise one. Notice our curve lies on that. And then finally, should make this red. Stand out a little bit more, make it thicker. Okay. And finally, we have another cylinder, another sinusoidal cylinder in the YZ, in the x direction. Let's see what that green is. There we go. Okay. So there's that green one coming out at us. That's y equals 2 sine z. So how does the curve relate to those three surfaces?
It's the intersection of the three surfaces.
Yes, it's the intersection of those three surfaces because that curve is going to lie on all three of those surfaces and ends up being the intersection. So we got two like vertical sinusoidal cylinders, and then this this elliptical cylinder looking straight down the elliptical center. And so our curve lies on all three of those, or is the intersection of those three. So what we're going to do now is we're going to start with equations like this. So given two equations, we know that are given two equations of surfaces. Where they intersect will form a curve. And so those equations will allow us to build the vector function for the curve. So we're going to kind of do what I just did, but in reverse. Now I'm going to give you some surfaces. Based on those surfaces, we're going to try to write the vector function for the curve of intersection.
Kind of neat at that the cylinder, like on the inside is just like you can only adjust one of the lengths, z, to really keep it the same, but you could adjust the I guess sinusoidal cylinders,
Mhm.
and rotate them because they could be really anywhere 360 degrees around that cylinder.
Yeah, but they'd be there would
They'd be different, yes.
Yeah, but yes, there would be sinusoidal cylinders that would apply like kind of all the way around. You're right. But they would be any one of those would be very complex and difficult to write.
Yes,
But
I'm sure they would be.
The ones that are parallel to these, the x and the y axes, these two are very simple, right? Very simple. Okay, so let's try a practice problem here. Let's do 15.5. So here are two surfaces. Y squared over 4 plus z squared equals 1, and z equals negative x plus 1. So we want to sketch these surfaces first. Try to imagine the intersection, so you can kind of predict what the curve will be, and then write that curve formally as a vector function.
Is this the curve of the intersection?
Yep. Well, these are two surfaces. Our goal is to write the curve of the intersection of the two. Does that make sense?
So that first function makes a circle on the YZ, correct?
Okay, is it a circle?
Ellipse.
So this 4 makes it not a circle anymore. So it's almost a circle, but then that 4 makes...
Yeah.
So makes in the y direction twice the radius of 2 versus a radius of 1 in the z direction. So something like this. Okay? And that's in the YZ plane. So is that what this equation is? It's a circle like that? Or an ellipse? Is that what the equation is?
It's a cylinder.
Elliptical cylinder, right? Cylinder. If x is absent, then x can be anything. Right? If x is absent, x can be anything. So we run this ellipse along the x-axis to create like a tube, right? An elliptical tube or elliptical cylinder this way. Something like that. Okay, what about this? What is this thing in R3?
Line. Line.
Is it a line?
On 3, so it's a plane.
Right, so in R3, so it would be a line just in the xz plane, but in R3, y is allowed to be anything. So y, so this is like, you would never really call it this, but it's like a linear cylinder. What is a linear cylinder? What do we know that
A
as?
set of plane?
That's a plane, right? And so x plus 0y plus z equals 1 has orthogonal vector, what? What's our orthogonal vector to that plane?
101.
Thank you. 1, 0, 1, right? The coefficients of x, y, and z are orthogonal vector. And so in terms of sketching it, we could, sketching it kind of thinking of it as a linear cylinder is maybe the easiest way. So z equals minus x plus 1, we could sketch in the xz plane. So it would be go through 0, 0, 1. And then in the xz direction, in the xz plane, we'd have a slope of negative 1. So like something like this. But then y can be anything. So then y...
And we're saying intersection of the surfaces, right?
Yes. So now what we want to do is we want to try to write, so when this slanted plane cuts through this elliptical cylinder, what kind of thing do we get? Can you imagine what you will get?
2 parallel lines.
Not quite.
Oh,
An ellipse.
Yeah, so think about this as being like a pipe, and you're just
would you
going to
get a
take
half
a,
ellipse?
you're going to take a
You would just
slanted
plane
plane, and you're going to slice through
that. Yeah,
that.
so
Oh,
just it's a plane, but it's just limited to the area that it touches the cylinder.
Oh, I see. Okay. So it's going the whole way through.
It's going the whole way through, right? It's gonna go the whole way through. And what will you get when you slice that thing? When you slice this.
Would it be circular?
So maybe. So we don't know, right? So because you're slicing on a slant, now you're going to get a longer axis here, right? So it's going to be something like this.
Would it be the circle that lies on that plane?
Well, you're either going to get a circle or some sort of an ellipse,
Right,
right?
exactly.
I don't think you can get anything else.
Right. Right, exactly. We're gonna get a circle or an ellipse. Circle would have to be the special relationship between this ellipse and the slant of this plane. Could possibly get us a slanted circle. Possibly. We know for sure it'll be an ellipse or a circle. Okay? So we're gonna figure this out. We're gonna actually put these together and come up with a vector function that meets both of these relationships between y and z and x and z, and then that vector function will show us that curve of intersection. So let's show the pretty picture. First, let's do blue. So here's what I was trying to draw. Hopefully you had a mental image correctly of it. So then, can you see there's the intersection in there? It's this right here. So maybe that's a circle. Maybe it's definitely a planar. It's definitely a planar curve because it lies in the blue plane, right? Because it lies on the blue plane. It's definitely planar. But the question is it an ellipse or a circle? So let's write the vector function here. So let's look at this first. How do we bring t into this? How do we parameterize? Bringing t into it is parameterizing an equation. How do we parameterize this ellipse?
Would we make x equal to t?
There's no x here.
Yeah, x, there's no common ratio, right?
You can replace
Because
one of
x
the
can be
variables
anything
with
in that.
one with sine t.
If we have y and z in an elliptical cylinder or an ellipse, what's the natural way to parameterize that? Someone said it.
Cosine t plus sine t.
We want cosine and sine. We want cosine and sine. That's the natural way.
2 sine.
So we'll do y equals. Someone said 2 sine t. I think that's a good choice. And then z would be
Cosine.
Cosine t.
cosine t.
How can you tell which one is sine and which one is
You could
cosine?
you could do it the other way. So you could do
Okay.
cosine and sine if you want. I could do minus 2 sine and plus cosine. There's 8 combinations of plus or minus sine and cosine that we could assign to y and z. And
Okay.
they would have different starting points and different directions of generating the curve.
The reason that we did not use full sine t rather than 2 sine t.
Because this is the radius squared. This is y squared over the y radius squared. And to get a y radius of 2 with sine t, you just multiply by 2.
What would x be?
Yeah, so now the question is, what would x be? Well, that's where this comes in. What does x equal? X equals
1 minus z.
1 minus z. Therefore, x equals
1 minus cosine t.
1 minus cosine t. So we got it. X is 1 minus cosine. Y is 2 sine t. Z is cosine t. That parametric function agrees with this cylinder in the yz and agrees with this cylinder in the xz.
And now you have your relationship between the different variables.
So I did it differently here, so I'll just... So notice here it's 2 cosine t and z is sine t, and that's perfectly legitimate too. But I'll switch it back to what we said, just so you're convinced that it's the right thing. All right, so do we have it?
You
We
have
also
to
have
change x.
x
I think
equals
you need to
minus
flip
cosine t.
sine t to cosine t, right?
Are we good now?
Yes.
Here we go. So we got it. It's that thing. So it's either a circle or an ellipse. I really can't tell. So I'm looking. It's kind of hard to tell. Looking straight at the. I think it still looks like an ellipse to me. I think it's
Yeah,
still.
most likely an ellipse.
Yeah, I think it's still an ellipse. But there would be some angle here of this plane that would actually generate a circle, a slanted circle that's on a slant in that plane. So I don't know what angle we would need for that plane, but there would be some plane there that cutting through this particular elliptical cylinder would actually generate a circle there.
Wouldn't it have to be orthogonal to, like, the plane vector would have to be orthogonal to, like, the direction that the cylinder's pointing?
Not necessarily, right?
No, because that would be a vertical plane. It has to do with the ratio of these radii. So something to do with the ratio of this radii would determine at what slant we would need this plane to actually make a circle. But I do want to do one more example. So any questions on this example?
Yeah, Professor, real quick.
Yeah, sure.
So does sine and cosine, are they interchangeable in the y and z?
Yep, they are. In fact, you could use you can use plus or minus sine and plus or minus cosine creates 8 combinations that would all work.
Because you can either have one and
That gives you
half,
4.
right?
That gives you 4 starting points and 2 directions for each starting point. So depending on how you pick plus or minus sine or plus or minus cosine for either of these, that gives 8 combinations that give 4 starting points and 2 directions for each starting point. Makes 8 possibilities.
Oh, okay, got it. Thank you.
Sure. All right, let's look at one more example. Uh, 14. All right, we'll try this one. So ignore this if statement there. Z is square root of x squared plus y squared.
What the fuck?
Hey Jacob, your microphone is on. So what is this? What do we have for that?
Is that a line?
Nope. So if we squared both sides, we'd have z squared equals x squared plus y squared.
Oh,
You'd
It's-
have a what was it? Cone with
Double cone?
hyperboloid. What was it?
Lots of guesses there.
Double cone.
Double cone,
You square both
but
sides and then get a double cone.
that's the double cone. If you square root both sides, you get plus or minus, which is the 2 cones. So this is a single cone. It's just the cone that opens in the positive z direction and not the one that opens down. Here's another plane, so let's graph those.
and it's because when you square it, it can be plus or minus, and you still get a positive.
That's right. So there's my single cone, and then here's my plane z equals 1 plus y, so that's plane in the y direction, in the zy. Based on a line in the yz plane running in the x direction, okay? And so when you see the x squared plus y squared, you might think, oh, okay, so I don't want that third equation. So you might think, oh, okay, we're going to use cosine and sine. And that's possible. It's possible you use cosine and sine, but we don't want to jump right into that because this relationship equals z. Okay, and because it equals z, we can't just jump right to cosine and sine. Right? If it were equal to a constant, then yes, we could set this up for cosine and sine. But not if it's equal to z, the third variable. So rather, we need to combine these equations. So since z is 1 plus y, we're going to put that right here. And we're going to combine and say 1 plus y equals square root of x squared plus y squared.
And then you can just square both sides, right?
That's a good thing. Do this fast. Square both sides. FOIL this out. 1 plus 2y plus y squared. And what do we notice here? Nice result. Y squareds go away.
X squared equals 1 plus 2y.
So y equals x squared minus 1 over 2. Is that a circle or an ellipse?
No.
It's a parabola.
Parabola. So because of that, we are wise not to choose x and y, right? So a sine and cosine. Our x and y relationship is not naturally defined by sine and cosine here. We have a parabola. Okay, so rather instead, we're going to use what I talked about earlier. How can I parameterize that most easily? I want to get t's involved here. I need x as a function of t and y as a function of t, so that this is the relationship of x and y.
X equals t.
Right? X can be t, and then y is...
Y equals t squared minus 1 over 2.
That's right. Remember having that earlier in class? So when you have a simple function, one variable is a function of another, and it's not a sine or cosine situation like a circle or an ellipse, then you can simply make t your independent variable, and then the dependent variable is just the same rule with a t in there. And now what was z? 1 plus y. So I can do 1 plus t squared minus 1 over 2. Okay.
Yeah, I have a question.
Sure thing.
Sorry. So where did this? I see there's 2 dx
this is
squares
our
in there.
parametric function.
dy
is mdx, so the curve of intersection,
equals
and
mdx.
Seems to be parabolic, right? So
And
we're
got-
squaring it. So you're gonna be
Parabolic
squaring
equation.
mdx.
Oh, okay.
You
Yeah,
see it?
I see it. Thanks.
Cool. So there's the curve of intersection. Because the angle of that plane is the same angle as the angle of the cone, it doesn't cut through and make a circle or an ellipse. It actually creates a slanted parabola in space. And here's the function for that, which came from, which came from our z equals the cone and the blue plane. All right, questions? Sorry, I'm going a little late here. I want to get through that example.
If we look at it directly from the x-axis, does it not have just a slope of 1?
Yeah, exactly. So why we don't see x?
Shouldn't the intercept point be 0?
So what we'd have to do is have to solve these two together. Well, so
Okay.
no.
Oh, okay, I see.
Well, no, it is. It's already solved. Z equals 1 plus y.
Yeah. Okay, I see now.
So there's no parabola there. It's just a line, and you see the line right there. There it is.
All right, I see. Thank you.
You're welcome. Any other questions?
Do we have a quiz?
We do not have a quiz today. No
Great.
quiz. So we'll call it there. Your next homework is due Thursday night. It's open. You can get started on Thursday night's homework. I will stick around right now for questions if anyone's got questions. Have a good day. See you Wednesday.
Have a good day.
You go over how you parameterize z. Oh, well, that was after you got y. You just subbed in.
Yeah, so once we had y, then z, we used the other equation, z equals 1 plus y. So just added 1 to y.
Okay. I guess then like how you figured out that x is t, is that just based on the slope, like the slope being 1, so you just subbed in t?
No, because I had y equals x squared minus 1 over 2.
Oh.
Because I had y as a function of x, the easiest route to take is to make t your independent variable in that function.
Okay.
And then y is just, you just write it down with t instead of x.
So would we always have problems that you're able to break it down to a point where we have one of the either x, y, or z, like one of the dimensions that can be turned into an independent variable and just sub from t?
No, the previous example didn't have that, remember?
Oh yeah, but that was like a circle or an ellipse, so then you could use like the sine cosine logic.
Right. So those are the two structures we've seen so far.
Okay.
If you have a function, one variable is a function of another, and it's not, it's not circular or elliptical, you can just use t for the independent variable. So that's kind of one strategy. But
Okay.
if you have two variables together and it's clearly a circle or an ellipse, then the natural way to do that is with cosine and sine. Don't set one of them equal to t.
Mhm.
Or you'll have square roots and plus or minuses, and that won't be good.
Okay. All right. Thank you.
You're welcome.
Yeah, what we call this one here a single cone. I still not wrap my head around that one here.
Sure. Okay, so do you see if I square both sides, I get this equation?
Yes, I see that one.
And do you remember that this was our reference double cone? This was when we did double cones right before the test. We called this our reference double cone. Do you remember that?
Yes.
So if I were to solve for z, what would I get? If I solved this for z, what would I get? Z equals what?
Square root.
But more to it, not just square root.
X squared plus y squared.
Okay, but that's not all I would get. Remember what happens when you take the square root of both sides of an equation?
Yeah, plus and minus.
Plus or minus, right? And what was this? This was a double cone, right? There's the cone where z is positive and the cone where z is negative. So that's what you're seeing right here. This is the upward opening cone where z is positive. This is the downward opening cone where z is negative.
Okay.
So what was given was just this, right? So what's given? This one only.
Yes.
Is that better?
Yes, I kind of see where you got.
Yeah.
Thank you so much.
Okay, you're welcome.
For like the equations we get, like when you give it to us, how do we know? Like obviously the first one, like a cone. Do you just know that because you can't really plug it into a graphing calculator with y squared? Do you just?
Yes. So we had a repertoire of surfaces that we have to know.
Okay, got it.
Paraboloids, double cones, ellipsoids, spheres, cylinders, planes.
Got it. So just memorize that, and I should be. Good.
Yeah. Memorize all the surfaces and their equation to their surface. Yep.
Okay. Thank you.
Yeah.